So here we are, Hodgepodge, part 3. Let's get after it. Okay, so what are the objectives for this third part of Hodgepodge? Well, we're going to do a redox review, which means we're going to take a look at how do we assign redox numbers and uh, go through all of that. This is a replay of Chapter 8, Section 9, and if you're familiar with this and comfortable with it, you can actually just skip that part and go to the next thing that we're going to be doing, which is balancing redox equations, because these things just don't happen by themselves. There's a whole reason why we assign these numbers, because we're trying to figure out who did what. And previously we looked at trying to figure out who underwent oxidation and reduction, but we were looking at unbalanced equations in doing that. So now we're going to see who underwent oxidation, who underwent reduction, and balance these, and we're going to do it in an acidic solution, and we're going to do it in a basic solution. So if that's new information, then go ahead and skip forward to the part that's 19.2. It's about 20 minutes in, so I don't have a timestamp for it yet, and I'm not going to make one, but you can skip ahead about 20 minutes and just go to the new material if you want to. Okay, oxidation and reduction reactions. What does that mean? Well, oxidation and reduction reactions describe a scenario when you have the transfer of electrons in the process of a chemical reaction. And oxidation and reduction occur together. Basically what that means is that somebody's given up the electrons and somebody's finding them. And we've talked about this when we talked about ionic bonds. Let's see if my example's right here. Okay, so let's say that we had potassium and we had chlorine coming together to create potassium chloride. Well, this should not come as any surprise that calcium has 1 valence electron and chlorine has 7. And that in order for these two substances to come together, they're actually going to create an ionic bond, because potassium is going to form an ion with a positive 1 charge, and chlorine is going to form an ion with a negative 1 charge. Now, how do we get that positive 1 on our potassium? Well, it's going to lose that electron, and it's going to end up creating that positive 1 ion. And chlorine, well, chlorine found that electron, and as a result, it's going to create an ion with a negative 1 charge, because remember, electrons carry with them a negative 1 charge. So here we have our potassium with a positive 1 charge, indicating that it has lost an electron, and there's our chlorine with a negative 1 charge because it has found that electron. And that when we put these two together, that's how we end up creating the ionic bond between potassium and chlorine. So redox reactions help us track this. But instead of drawing out the Lewis dot, we actually do it through a numbering system whereby we assign something known as oxidation numbers. So again, to reiterate, oxidation and reduction reactions, redox reactions as they're also known, are reactions where electrons are transferred from one atom to another. Atoms that lose the electrons are being oxidized. So in our example here with potassium, potassium would be the one that is being oxidized. And the atom that finds that electron or gains the electrons are the ones that are being reduced. And my example here, we have chlorine. Chlorine was the one that was reduced. So that's the language behind all of this. And let's put it to work. Just like that. So how do we set about quantifying a redox reaction? How do we get some data so we can do some analysis and figure out what the heck is going on with this thing? Well, what you're going to do is you're going to assign what's known as an oxidation number to your redox reaction. And it's going to, each element or polyatomic ion is going to end up getting an oxidation number. So let's bring up an equation and see what I'm talking about. All right, so here we have a molecular equation, and what's happening here is that we've got a solid zinc and an aqueous solution of copper sulfate. Going to mix those together, and what's going to happen is zinc sulfate is going to form. It's actually going to ionize, and then we're going to end up having our copper drop out of solution and form a solid. Now, in order to assign the oxidation numbers, I'm going to write this as an ionic equation. So what I've done here is I've left zinc solid as it is, but I've taken the copper out of the copper sulfate. And so I have copper, and then I have the sulfate ion. And I'm going to leave the sulfate ion as a polyatomic ion. It's easier to work with this way. And then on the other side of the arrow, we have zinc as an ion and sulfate as an ion, and then copper as a solid. Now I'm going to assign the numbers. I'm going to assign the numbers without telling you how I'm coming up with these numbers first. But in a minute, we're going to look at how to come up with these numbers. And then we're going to do plenty of exercise around coming up with these numbers. All right, so zinc as a solid is going to get an oxidation number of 0. Copper is going to get an oxidation number of +2. Sulfite is going to get an oxidation number of -2. Now these positives and these negatives are basically telling us about the movement of electrons, or the state of affairs with their electrons. And the inclination is to think of these as being the same as the charge, but it's not really. The charge is basically telling us about the state of affairs with our electrons, and the resulting charge, oxidation numbers, tell us about the state of affairs of the electrons. So and the accounting system that's built around it. I know it sounds crazy. It looks the same, and at this point in the lecture, we could probably say it looks the same and we're going to go with it. Don't tell anybody at IUPAC, they'll come and get me. All right, so what's happening on the right side of the transformation arrow? Well, we have zinc, and it's going to have an oxidation number of +2. Our sulfate's still going to have a -2, and our copper solid is going to have an oxidation number of 0. All right, let's take a look at what happened to zinc. So on the left side of the transformation arrow, zinc had a oxidation number of 0, and on the right side of the transformation arrow, that went to a +2. So what happened to zinc is that it gave up a couple of electrons to sulfate, essentially, and it became an ion of itself. So when you lose ions, you undergo oxidation. All right, let's take a look at copper. What happened to copper? Well, copper went from a +2 to 0. So in this case, what happened to copper is copper found a couple of electrons and returned to its ground state where it doesn't have any charge. And because it had a reduction in its oxidation number, we would say it underwent a reduction. So because we had an increase in the oxidation number for zinc, it underwent oxidation. And because we had a decrease in oxidation number for copper, it underwent what's called a reduction. Now the language in the lecture in the book gets a little funky. I'm going to use it right here. An agent that undergoes a reduction is an oxidizing agent. The agent that undergoes an oxidation is a reducing agent. So it's like if you do the thing, then you're the agent of the opposite. So yeah, if you do the thing, oxidize, then you are an agent of the opposite, which means you're a reduction agent. Okay, I hope that makes sense. So how did I come up with those numbers? Well, I'm sure there's a very wordy explanation in the book. I've come up with a chart that I think is pretty simple to utilize, and here it is. So first thing, if you have an element by itself, the oxidation number is 0. If you have an element by itself, it's typically in its ground state. So it's not going to be at a loss for electrons, nor has it gained any. So its oxidation number, it's going to be 0. If you are a group 1A element in a compound, it's going to have a +1 oxidation number always. If you're a group 2A, you will have an oxidation number of +2 when you're in a compound. If you are group 7A, usually you're going to be a -1 for an oxidation number, unless you're with oxygen, in which case you will be a +1. All right, so that's part of it. There's more. There's always more. And here it goes. If you are a monatomic ion, such as calcium or magnesium, then your oxidation number is going to be the same value as your charge. So where you have a charge of 2+ for calcium, the oxidation number is going to be +2. Okay. If you're hydrogen, it really depends on who you're coupled up with. If you're coupled up with a non-metal, then your oxidation number is going to be a +1. If you're coupled up with a metal, then your oxidation number is going to be -1. If you're oxygen, your oxidation number is usually going to be -2, unless you're in with hydrogen peroxide, in which case your oxidation number will end up being a -1. But that would be a special case. And if you are fluorine, your oxidation number is always a -1. Okay. And there's a couple more. The sum of oxidation numbers for any neutral compound has to equal 0. So if you have two elements in your compound, then the addition of the sum of their oxidation numbers has to equal 0. The sum of oxidation numbers for polyatomic ions are going to be equal to the ion charge. These are the rules. I like writing them this way because it's real easy to see. Not very wordy. It's just right there. So let's try our hands at it. So let's bring up one. We have carbon. What rule are we going to use to assign an oxidation number for carbon? Well, carbon is an element by itself, which means its oxidation number is going to be 0. All right, let's do another. Oh, what do we have here? We have aluminum with a floaty +3. Well, that would mean aluminum is a monatomic ion. And what's the rule for monatomic ions? It gets the ion charge, which means that the oxidation number for the ion of aluminum is a +3. Oh, what about aluminum in the ground state? Well, in this case, it's not a monatomic ion. In this case, it is an element by itself, and its oxidation number would be 0. What if we had magnesium by itself? Magnesium is a group 2A, but it's an element by itself, so it ends up getting an oxidation number of 0. What if magnesium was in a compound like magnesium oxide? Well, now we have the rule that says the sum of oxidation numbers for a neutral compound has to be equal to 0, which means that magnesium is going to be doing something and oxygen is going to be doing something, and they're both going to have some sort of an oxidation number. Well, the rule for magnesium says, because it's group 2A, that it's always going to be a +2. That is when it's in a compound or in its ion state. And oxygen is always going to be -2 unless it's in hydrogen peroxide, which is not. And we can see that the +2 of magnesium and the -2 of oxygen is going to be equal to 0, and that fits the rule that says the sum of the oxidation numbers for a neutral compound equals 0. So that's how that works. What if we had something like hydrogen chloride? Well, we'd have to look at the rule for hydrogen for starters. So hydrogen is going to be a +1 with non-metals and a -1 with metals. What is chlorine? Chlorine is a non-metal, so hydrogen is going to be a +1, and chlorine is a group 7A, and it's with hydrogen, not oxygen, so it's going to be a -1, and the +1 of hydrogen and the -1 of chlorine are going to come together and give us a 0 for the overall oxidation number because it's a neutral compound. What if we had something like water? Well, hydrogen is with a non-metal, which means that it's going to have a +1 charge, but we have two of them. We have two of them, and we have to take into account the fact that we have two of them. So we would take the positive one of just a single hydrogen and we would multiply it by 2. So the effect of hydrogen's oxidation numbers is going to be a positive 2, which is great because it offsets the oxidation number for oxygen, which is a negative 2, and we end up with a neutral compound with no charge. What if we had something like this, NO3? There's a rule for this, and it's called the polyatomic ion rule. And it says the sum of oxidation numbers for polyatomic ions is equal to the charge of the ion, and in this case, it would be -1. So this is how you apply those rules, and that is how I apply the rules for assigning the numbers in the equation that we first looked at. So let's take a look at this equation where we have lead and sulfuric acid coming together to make lead sulfate and hydrogen gas. Now that we know what the rules are, I'm not going to bother to tease out the ions. We're just going to go ahead and start filling in the oxidation numbers. So for lead, ground state lead, an element by itself, oxidation number is going to be 0. Let's look at hydrogen. So we have some rules for hydrogen. The rules say that if we are with nonmetals, we're going to have a +1 charge. Let's see, sulfur and oxygen, they are both nonmetals. So our hydrogen is going to be a +1. But how many hydrogens do we have? We have 2. So the overall oxidation value of our hydrogen is going to be +2. That's going to be important because when we look at what our sulfate ion is, it comes in with a -2. So we have a +2 and a -2. The oxidation numbers go to 0, which means that this is a neutral compound, which it is. I don't see any charges floating around it. So yeah, we're good with that. All right, let's take a look at lead. Well, lead is going to have to offset the -2 of our sulfate, which means that our lead is going to come in as a +2. See how I backed that in? I didn't know what lead was because lead could be 2 things. Lead could be a +2 or lead could be a +4 because lead can form 2 different types of ions. And not knowing which one it was, I had to look to something that I did know about in my formula, and I did know about sulfate. So that's how I did that. All right, what about our hydrogen gas? Well, this is technically a neutral compound, but the way we would get a neutral compound is if one of those hydrogens had a negative charge, which it's not going to. So when you have a molecule where you have 2 of the same element, like hydrogen or chlorine or nitrogen, the oxidation number on each one of those is going to be 0, and the overall effect is that you have a neutral compound, and the oxidation number will be 0. All right. So now that we've assigned oxidation numbers, can we determine who has been oxidized and who has been reduced? Of course we can. We can look and see what's happening. Who has changed? Well, the first thing we can see is that good old lead has undergone some sort of transformation. It went from a 0 to a +2. That means that it went through oxidation. It is the reducing agent. Now our sulfate stayed the same, but what happened to our hydrogen? Our hydrogen went from a +2, got my square wrong there, to a 0. Yep, and all my animations are wrong, but I'm going to leave it at this point because it's midnight and I'm tired. So yeah, we went from a +2 to a 0. So in this case, our hydrogen was reduced. It is the oxidizing agent. So that's what that tells us. This is what we're looking for. That's how we know who has been oxidized and who has been reduced. So why are we assigning these oxidation numbers? Well, the chemists do this. They are basically determining what's known as the oxidation state. And by determining oxidation state, it allows the chemist to determine the flow of electrons in the reaction. And as we've studied pretty much from the very beginning, it is the movement of those electrons that is driving bonds and all kinds of reactions. So understanding that flow is important. Now, This is basically a very elaborate accounting system that is helping us get some sort of an understanding, a concrete understanding about what these electrons are doing. So that's really what this is. It's just an elaborate accounting system, a contrived accounting system. So, and here's the slide that says, even though they look like them, oxidation states are not ion charges. Oxidation states are imaginary charges assigned based upon a set of rules, and ion charges are real. They're measurable charges. It shows what happens once the electrons show up or leave. So that's the difference. But you can actually use the ion charge to determine oxidation number, even though they're not the same thing. So there's that. As stated originally, oxidation and reduction must occur simultaneously. If somebody's being oxidized, somebody's being reduced. The reactant that reduces the element in a reactant is called the reducing agent. The reducing agent is undergoing oxidation. The reactant that oxidizes an element is known as the oxidizing agent, and the oxidizing agent is the element that is undergoing reduction. Hopefully that makes it clear. So up until this point, we have assigned oxidation numbers to elements and ions and polyatomic ions and neutral compounds. Now, these things enter into reactions, and what happens in these reactions is that the electrons are getting transferred from one atom or one element or one polyatomic ion or one compound to another. And whenever you have somebody undergoing oxidation, then you have somebody else undergoing reduction. So these two things happen together, and we can write equations that tell the story about what's happening here. So in the case of our sodium molecule and our chlorine molecule, they can undergo oxidation and reduction. And what we see here is that sodium has actually become a positively charged ion, and it lost its electron in the process, so it underwent oxidation. And here we can see chlorine actually gained a couple of electrons, and it underwent reduction. So we can figure this out in different sort of chemical equations, and that's what this section is going to have us do. So just to refresh, oxidation is a process when we see the oxidation number of an element increase. This is when the element is losing electrons. Typically what's happening is that compound is gaining oxygen. It might be losing hydrogen. And the electrons that are going to show up as products. So in the process of creating these balanced redox reactions, we're going to have to be adding electrons somewhere. And when we look at the oxidation portion of the reaction, because we're going to tease these two things apart in just a second, we're going to be adding electrons to the oxidation part of the reaction, but in the reduction part of the reaction, we're going to be adding it to the reactants side. You'll see that right down here. So what's happening in a reduction reaction is that the oxidation number is going to decrease. This is when we look at it going across the transformation arrow. This means that it has gained electrons. The compound has lost oxygen. It might gain a hydrogen, and it's also going to gain some electrons as part of that. So in order to balance a redox reaction, what you have to do is you have to isolate the oxidation portion of the reaction and the reduction part of the reaction, and then balance those and then bring them back together. So if we look at this reaction right here, what we can see is we have this chlorine and we have the iodine, and here chlorine's the molecule, iodide is the ion, and then across the transformation arrow, chlorine is changed, and now it's the ion. And iodine has undergone a change too because it's been coupled up with oxygen. And if we reassign oxidation numbers, chlorine got a 0 because it's a molecule and it has no charge to it. Iodide, the ion, has a -1 charge. Hydrogen always has a +1 charge, or sometimes when it doesn't, but it has a +1. Oxygen always has a -2, unless it's with hydrogen peroxide, which it's not in this case. And chloride always has a -1. And we can't figure out what iodide is, but we can figure out what oxygen is and then do some backwards calculations and figure out that iodine actually is now a +5. Oxygen is still a -2. Hydrogen is still a +1. So if we look at what happened between chlorines, we can see chlorine went from a 0 to a -1. So its oxidation number went down, which means that it underwent a reduction reaction. It gained electrons. If we look at what happened to iodide, it went from a -1 all the way up to a +5. So its oxidation number went up, which means it lost electrons. So this is how we would isolate the reaction for iodine, and this is how we would isolate the reaction for chlorine. So now we have our two half reactions. So balancing redox reactions by the half reaction method means that the reaction is broken down into the two half reactions, one for oxidation, the other one for reduction, and then each half reaction is going to be balanced, and you have to use electrons in order to do that. So we're going to be adding some things in like water and hydrogen ions and electrons. And then after you do that, you're going to balance the reactions for the atoms, and then you're going to put the two reactions back together. So there's nothing, it's kind of a bad explanation actually, and it gets worse on the next slide. Let's go ahead and look at that. So these are the instructions for that. These instructions are a little bit misleading, which is why I'm going to actually work a couple of these problems for you. So I'm going to go over these steps, and then I'll show you the steps as we work them. All right, so the first thing we're going to do is we're going to assign oxidation numbers to everything to figure out who has been oxidized and who has been reduced. And then we're going to write the oxidation reaction separate from the reduction reaction. And that's the first thing we're going to do. And then next, we're going to revisit this slide, and then we're going to balance the half reactions. And we're going to do this by, first of all, ignoring hydrogen and oxygen, balancing the other elements in the equations first. And then where there's oxygen that needs to be balanced, we're going to add water. And then by adding water, we add these hydrogen ions, which means we are going to have to balance the other side of the equation, where we didn't add water, with these hydrogen ions. And then after we do that, we're not going to do this just yet, we're going to balance these half reactions by adjusting with the electrons. So let's do these first two steps first. All right, so here we have silver and nitrate undergoing a reaction. And the first thing we need to do is assign oxidation numbers. So when we have an element by itself with no charge, it gets an oxidation number of 0. Now we don't always know what nitrogen is going to do, but we can know what oxygen is going to do. Oxygen is always going to be a -2. But we have 3 oxygens here, so we're going to multiply this -2 by 3. And the overall effect of these 3 oxygens is a -6. Now, whatever nitrogen is going to be, it has to offset -6 enough so that this ion ends up with a -1 charge. Well, that math should be pretty easy. That means that nitrogen is going to be a +5. So for the left side of our equation, we know the oxidation numbers for silver, nitrogen, and oxygen. Now, what about the right side? Well, here we can see that something has happened to silver. It's now got a +1 charge. We still don't know what nitrogen is going to do, but we can always pretty much guess what oxygen is going to do. It's going to be a -2. We only have one of them, which means that nitrogen needs to be able to offset that -2, which means nitrogen is going to be a +2, and we have the oxidation numbers for the elements on the right side of the equation. All right, so now at this point we need to figure out who's been oxidized and who's been reduced. So let's take a look at that. So we know that reduction is when the oxidation number goes down. Oxidation is when the oxidation number goes up. So if we look at what happens with silver, we can see it goes from 0 to 1, a +1. So its oxidation number went up, which means it underwent oxidation. Now, typically nothing happens with oxygen, and if we look at it, it's -2 on both sides of the transformation arrow, but nitrogen ended up doing something funny. Nitrogen went from a +5 to a +2. Its oxidation number went down, which means that it underwent reduction. So we have an oxidation reaction involving silver, and we have a reduction reaction involving our nitrate ion going to nitrogen monoxide. Now we're going to balance each one of these half reactions separately, and it takes 2 steps to do that. So let's get started with that. All right, so in order to balance these 2 equations, we're going to be looking at this part right here. We're going to balance everything except hydrogen and oxygen, and then we're going to take a look at our oxygens, and we're going to balance those by adding water where we need to. And by adding water, we'll also be adding hydrogen ions, which means, hydrogen, which means we're going to have to add these hydrogen ions in order to balance the hydrogens out. We're not going to worry about this. I'm going to point out something regarding this base reaction in just a minute when we get to that point, but not just yet. And then after we've balanced everything with hydrogen ions and water, then we have to introduce these electrons. So let's take a look and see what's happening there. All right, let's start with this one. So we're going to balance the masses. So we need to make sure that the same number of elements on the left side of the transformation also appear on the right side of the transformation arrow. So we know that we have 1 nitrogen, and we can see we have 3 oxygens. And on the right side we have 1 nitrogen and we have 1 oxygen. So we can see we have a problem. We don't have enough oxygens on the right side. So the way that we're going to do that is we're going to add a water molecule. Well, water molecules only have 1 oxygen, and we actually need to have another 2 oxygens in order to balance the oxygens on the left side of our equation. So we're going to double our water molecules. So now that gives us an additional 2 oxygens, and now we have 3 oxygens on the right side. But in doing that, we've also added 4 hydrogens, which means we have to come up with a way to add 4 hydrogens on the left. See where we're going? The way we're going to do that is we're going to add 4 hydrogen ions right there. Now at this point we have balanced the masses of the reduction reaction. Now we have to balance these charges that we see. So let's do that. So if we look at these 4 hydrogen ions, we know that that's going to give an overall effect of a positive 4. And we know that our nitrate ion has a negative 1. And if we add positive 4 and negative 1 together, we're going to get a positive 3. So the left side of our equation has an overall effect of a positive 3. On the right side of the equation, we don't have a charge. So how is it that we're going to get the positive 3 on the left to balance out with the 0 on the right? Well, now we can add our friends, the electrons, because electrons have negative charge. And if we add 3 electrons here, that will give us 3 negative charges, which will allow us to offset the positive effect of the other 2 reactants. And now we have balanced the charges of this reaction. And what we're going to move forward with at this point is going to be this reaction right here. Our 3 electrons, 4 hydrogen ions, nitrate being equal to nitrogen monoxide, and a couple of water molecules. Now let's do the same thing for our oxidation reaction. All right, so the first thing we need to do is balance the masses. Make sure that we have the same number of elements on each side of the transformation arrow, and that's actually pretty simple. 1 silver on the left, 1 on the right. All right, now let's move on and balance the charges. Okay, if we look at the silver on the left, we don't have a charge. If we look at the silver on the right, we have a positive 1 charge. How many electrons do we need to add to offset that? Well, we only need to add 1. And with this negative 1 charge, it now balances what we have on the left. That was pretty simple, wasn't it? And this is the equation that we're going to move forward with. So at this point, what we're going to do is we're going to combine these 2. So let's look at where we are on this particular set of instructions. All right, so we're at number 6 at this point. We're going to add the 2 half reactions together, so let's do that. All right, so these are our 2 half reactions, and we have those crazy electrons hanging out there. Now you might remember that one of the rules that we have when we're balancing equations is that if we have repeating terms on the left side of the transformation arrow and the right side of the transformation arrow, we can cancel those out. And we have these free floating electrons over here on the left, and we have just 1 on the right. Now, what would be ideal is if we had 3 on the left and 3 on the right. So how are we going to make that happen? Well, we can manipulate this, believe it or not. This is part of balancing equations. We can manipulate this bottom reaction by multiplying the whole thing by 3. So when we multiply everything by 3, that means we're going to have 3 silvers are going to be equal to 3 silver ions plus 3 electrons. And that gives us 3 electrons on the left in one equation and 3 on the right of the other one. So that when we add these together, we can actually cross those electrons out. So now let's combine our two equations. So I'm going to draw this line here just so we can keep straight what's happening. So we're going to take this 4 hydrogens here and our nitrate ion there and our 3 silvers, and that's what's on the left of the transformation arrow. And now we're going to combine all of these things that are on the right. So our nitrogen monoxide, our 2 waters, and our 3 silver ions. All right. Now the next step, step number 7, says that we need to just double check our work, and I like to do that. So let's do that. So let's see. We start off right here. We have 4 hydrogens. We have 1 nitrogen. We have 3 oxygens, and we have 3 silvers. All right. So how many hydrogens do we have over here? Well, we've got 4. That works out. 1 nitrogen. That looks good. Oxygens. Here's 1. Here's another 2. All right, that makes 3. And then here's our 3 silvers. All right, that worked great. So what did we do here? We ended up adding water. We added hydrogen ions. And we added electrons to offset everything. Once we got rid of our electrons, we were left with these hydrogen ions right here. Overall, then, what we're dealing with is balancing a reaction in an acidic solution, because what we ended up with is these acid with these free-floating hydrogens, and they make a solution acid. Now, the other possibility is that we would want to balance a redox reaction that's occurring in a basic solution. And in order to do that, we're going to do all the steps that we just saw up until this point, and then we have to do a couple more steps to get rid of any hydrogens that we have left. So let's work one of those problems right now. All right, so the first thing we're going to do is we're going to assign oxidation numbers and figure out who got oxidized and who got reduced. So zinc is a free-floating element. It gets a 0 oxidation number. We don't know anything about nitrogen, but we do know about oxygen. It's always -2. We have 3 of them, which gives the overall effect of a -6. Which means that nitrogen must be a +5 so that our nitrate ion ends up with a -1 charge. And with that, we know the oxidation numbers for our reactants. Now on the right side of the equation, here we have zinc with a +2. So the oxidation number is going to be equal to the charge of the ion when you have that scenario. We don't really know what's happening with nitrogen, but we do know what's happening with oxygen. Oxygen's -2. But we have 2 of them, so we have to multiply that by 2. So we have a -4. So the effect of oxygen is going to be -4, which means that nitrogen must be a +4 to offset it. And now we know the oxidation numbers for our products. So let's take a look and see who got reduced and who got oxidized. So we know that reduction is when oxidation numbers go down. Oxidation is when oxidation numbers go up. So if we look at what's happening with zinc, zinc went from a 0 to a +2. His oxidation number went up, so it was oxidized. Let's take a look at nitrogen. Nitrogen went from a +5 down to a +4, so it got reduced. And we can tease these two things apart, and here is our oxidation reaction, and here's our reduction reaction. So let's balance these using the 2 steps that we learned, balancing the masses and then balancing the charges. All right, so we're going to be doing this, but now we're going to be having to take a look at this as we move through the next few steps. And we're still going to be doing that. All right, so let's do that. All right, let's balance the masses. So we have 1 nitrogen, 3 oxygens, 1 nitrogen, 2 oxygens. So what do? We're going to add a water. Water gives us the 1 oxygen that we need, and now our oxygens are balanced. But we've added a couple of hydrogens to the right side, which means we need to add a couple of hydrogens to the left side, and we do that by adding 2 hydrogen ions. So we've balanced the masses. Now let's balance the charges. So our 2 hydrogen ions are going to give us a positive 2. Our 1 nitrate ion is going to give us a negative 1. And when we add those two together, we're going to end up with a positive 1 overall on the left. On the right, we have no charge. So how are we going to offset the positive 1 on the left? We're going to do that by adding an electron. That 1 electron is going to give us a negative 1, and it allows us to reduce that positive 1 to a 0. So now we have balanced the masses and the charges of our redox reaction. So now let's do the same thing for our oxidation reaction. So we have to balance the masses. That's pretty straightforward. We have 1 zinc on each side. Let's balance the charges. So the zinc on the left has 0, the zinc on the right has a positive 2. We balance that by giving it 2 electrons. Those 2 electrons give us a negative 2, and we have now balanced the charges. Now at this point we want to combine our two balanced half reactions. So here we go. Now really what we're looking for at this point is we want to see what do we have with regards to these two free floating electrons, because we want to get rid of those before we combine everything. I think it's easier just to get rid of them at this point. But we can see that we have only 1 in the top equation and we have 2 in the bottom. Well, that means we're going to have to multiply the entire top equation by 2 in order to get those electrons to balance. So let's do that. So we have 2 electrons. Now we have 4 hydrogen ions. We have 2 nitrates, and we're going to have 2 nitrogen dioxide and 2 water molecules. Let's get rid of this because I don't want to confuse us with what we got going on. All right, now we can get rid of these 2 electrons. Now let's combine these 2 equations. So we're going to have our 4 hydrogen ions, our 2 nitrates, our 1 zinc on the left, and on the right we're going to have our 2 nitrogen dioxide, our 2 waters, and our 1 zinc. All right, this is great, but we have a problem because this is supposed to be in a basic solution, and if we look right here, we have something that is leading us towards an acidic solution. So now we have to do a couple more steps to get this out of the acidic state and into the basic state. So let's do that. All right, so in order to get rid of these 4 hydrogen ions, what we're going to do is we're going to add hydroxide. And the rule is this. You're going to add a hydroxide to both sides for every hydrogen ion that you have. So we have 4 hydrogen ions on the left, so we're going to add 4 hydroxides on the left, but we're also going to add 4 on the right. All right, so what happens when you add hydroxide and hydrogen together? Well, you're going to end up with a water molecule. So I'm going to rewrite this showing that I now have 4 water molecules on the left. Everything else stays the same. Oh, but now we have some repeating terms because we have water on the left and we have water on the right. Well, we have 4 waters on the left and we have 2 waters on the right. So that means that 2 waters on the right are going to go away. And we're going to take the 4 that we had on the left and we're going to reduce that to 2. So now we have 2 waters on the left and 2 nitrates, 1 zinc, 2 nitrogen monoxide on the right, no waters, our zinc, and our 4 hydroxide. And this is good because now we're in a basic solution. Now, I always like to check my work at this point because I got to tell you, when I was working through this, setting up these slides, I actually did it wrong. And by doing this check, I realized it. Otherwise, it would have been a disaster. I tell you, a disaster. So let's just go ahead and double check and make sure I did it right. So let's see. Let's start with this right here. So we have 4 hydrogens, and let's do oxygen next. So we have 2 here, and we have 6 there. So we have 8 oxygens, 1 nitrogen right there, 1 zinc. Looks good. All right, over here, let's look at our hydrogens on the right side. We got 4 hydrogens. Looks pretty good. Let's see, oxygens, we should have 8. Let's see, there's 2 times 2 is 4. And here's another 4. That makes 8. Looks good. There's our 2 nitrogens. And there's our zinc. Bam. That looks great. So, yeah, to balance a solution that is basic, the same steps, except you got to get rid of those hydrogens, and you do that just by adding enough hydroxide ions to turn those hydrogens into water and then cancel out the waters, because you're going to have duplicate waters on the left side of the equation as on the right side. And that's it. And with that, we are done with the hodgepodge.